In this video, we start the process of thinking about how all the different methods we have for computing integrals work together and how will allow us to choose which method is most appropriate for a given problem. So this set of videos sort of aims to conjoin everything that we've been doing so far. All these methods we have for integration, how can we think about them as a whole and as a process of problem solving to figure out which integral is appropriate for a given situation. So what are the big classes of methods that we have for solving these problems? Well, we have algebraic simplification, we have substitution, we have integration by parts, and we have other sort of special techniques that I'll sort of clump all together at the end here. So what do we mean by algebraic simplification? This is the idea of converting an expression into something that's easier by canceling polynomial terms or factoring things out, things like that to make the expression easier to handle. Substitution is clearly the normal substitution method where I have a u and a du and I'm plugging those in to simplify my problem. Integration by parts, it should be fairly self-explanatory. It is when I have a product that I want to solve using the integration by parts technique. And then special techniques have a sort of list of things we've been doing for the rest of this chapter. These are things like trig integrals, powers of sine and cosine, powers of secant and tangent. We have trig substitution, handling things with like radical a squared minus x squared, things like that. And then things like partial fractions. The idea being these last three have very specific circumstances in which they become important. They're super important when they show up, but they only appear in certain situations, so it's easy to figure out when those do and don't apply. And the point here is to figure out what do all these do, how they relate to each other, and how can I use that to help me solve a problem. So the first technique is algebraic simplification. The idea here is basically using your normal polynomial algebra to simplify things, cancel things out, work with exponents, things like that, to make it so you can actually integrate the expression. This isn't necessarily an integration technique, it is the way you approach the problem to then make it so it's easier to integrate the problem. Here's an example of that. I want to compute the integral of x to the fourth plus 3x plus 5 over x to the 3/2 dx. What you want to do here is this I can't integrate directly, but I can distribute that x to the 3/2 to every term because it's in the denominator of the entire fraction. And then if I put the power on every term, then it just becomes an expression that I can just integrate directly. I can rewrite this as x to the fourth over x to the 3/2 plus 3x over x to the 3/2 minus 5 over x to the 3/2 dx based on normal fraction manipulation. And I can simplify this out. 4 is 8/2, this is x to the 5/2, 3x to the minus 1/2, minus 5x to the minus 3/2. And now these are all integrable. And I get that from antiderivative. So that's just the idea of this first step is what can I do from an algebraic point of view to simplify exponents, to cancel some things out, to move some things around, to make it so that I can integrate the function. That's our first and easiest technique. It's probably the first one you want to think about is can I make this simpler just using algebra to then give me something that I know how to integrate.